talk. Hasan will be talking about understanding Hartman effect, possible role of PT symmetry. Hasan, please continue.
Okay, sorry. Yeah, good morning to everybody. Thanks to the organizers for the invitations to deliver this talk. Uh, I will be talking on this understanding the Hartman effect and its possible role for the PT symmetry. The Hartman effect may be new for most of the people because the Hartman effect has been the subject of the studies for the real system. But in this talk, I will be showing that how the PT symmetry may be responsible for the occurrence of this Hartman effect. So as you know that the tunneling phenomena is one of the best studied phenomena of the quantum mechanics, and it is one of the earliest studied problem of quantum mechanics. However, how much time does a particle takes to tunnel through a potential barrier? It is still an open problem, both theoretically as well as experimentally. Now consider this system here, a localized Gaussian wave packet which is incidence on a potential barrier here. For the simplicity, I have put it as a rectangular potential barrier, but this is the argument. The subsequent argument will be valid for any finite range regular potential. So this Gaussian wave packet is localized at wave number k equal to k0 and is incidence on the potential barrier here. And as it tunnels through the barrier with the transmission coefficients written here, the Gaussian wave packet is perturbed in the following fashion, and it picks up a phase factor phi here. And this gets modulated because of this transmission coefficient here. So the emergent localized Gaussian wave packet is still centered around k equal to k0, but it's different than the previous one because of this transmission coefficients here. Now, as per the stationary phase method, defines the tunneling time tau as the time taken by the wave packet, the peak of the wave packet to emerge across the other side of the potential barrier. The tau is a time when the peak of the wave packet is seen on the other side of the barrier from this side to this side. And if you do a little algebra on this, based on these definitions, you will find that the tunneling time tau is defined as the phase delay time plus the time taken to cross the free propagation time, which is this h cross k by m is nothing but the velocity, the momentum divided by the mass. This is b upon velocity. So this is the velocity of the Gaussian wave packet here. So b upon velocity is the free propagation time, and this gets added up with the phase delay time, and this defines the total net tunneling time for the system here. So as you see this, yeah. So if you apply this simple argument for the case of this rectangular barrier, what you will see that the expressions for the tunneling time as according to the stationary phase method turns out to be like this, where I have the k is equal to root over e, q is equal to root over v minus e, and I have taken the units as 2m equal to 1, h bar equal to 1, and c equal to 1. Because of this hyperbolic function here, if you take the b tending to 0, I mean the thickness of the potential barrier is very small, but you will see that in this limit tau is 0, which is expected because when the barrier is null, if the barrier is not present there, then the tunneling time is 0. But if you see this b tending to infinite, or b is large actually, because of this tan hyperbolic qb will quickly saturates with respect to b, and the dependence of b will be totally lost from this function. So for the large b, what you see is that the tau tunneling time tau becomes independent of the thickness of the potential barrier, and this result is highly unexpected. In terms of this unit, the limit b tending to infinite for the large b, the tunneling time tau is simply equate to 1 upon qk, and this does not depends upon the b. So this is the problem here with respect to this tunneling time. And you can see from this figure that the saturation of the tunneling time, it very quickly happens with respect to the thickness, because as you know that this tan hyperbolic function is the exponential dependence, and it's very quickly it quickly saturates to 1 for the larger b actually is. And b need not be close to infinity, it's very quickly saturation. So for example, from here you can say that when b equal to 10 and b equal to 20, the particle doesn't take time to tunnel from this side, from this region. And this has been a paradox since 1962, when this was first noted by Hartman in the year 1962. So for sufficiently opaque barrier, the tunneling time is independent of the thickness of the barrier. And this is true happens only for E less than V, when the energy of the particle is less than the height of the barrier. The reason for this Hartman effect is not known yet that why it occurs actually this. There are the arguments that some reshaping of the wave, some acceleration mechanism inside the barrier may be responsible for that. So I will not go into the details of this. I mean, I will suggest that the interested readers can go through the Winful articles on this Hartman effect. When we see this, the Hartman effect has also been calculated for the case of this non-Hermitian system. So when the system is taken as V1 plus I V2 type of a complex rectangular barrier of finite thickness B, in this case, it has been shown that tunneling time in this case always depends upon the thickness of the barrier, and there is no Hartman effect in this case. However, we calculated this for the case of the PT symmetric system. We considered this system as U plus IV and U minus IV of equal thickness on the both sides on the origin. And you can see that this system is one of the simplest system for the PT symmetry, representing the PT symmetric case. And when you calculate the tunneling time from this system, what you will note that it does not have in the limit of this B tending to infinite, this term is totally independent of the thickness of the barrier. And Hartman effect does occurs for this PT symmetric system. So here is a sort of this puzzle that I mean, in both this example, if you see that the tunneling time is calculated for the non-Hermitian system, and when the system does not respect the PT symmetry, you have this Hartman effect. But when the system respects PT symmetry, when the system does not respect PT symmetry, the Hartman effect is not there. And when the system respects PT symmetry, then the Hartman effect occurs actually this. So we decided to investigate this further, and we considered a system at the symmetry breaking threshold. We decided to investigate the presence of Hartman effect at the symmetry breaking threshold. So we considered the system like this, U plus IV and U minus I epsilon V. This system does not respect PT symmetry when epsilon deviates from unity, but when epsilon equal to 1, this is the same system as we considered in the previous slide. And what we did is that we calculated the tunneling time from this system. We took the limiting case of B tending to infinity and expanded the expressions. Expanded this expression in the form of Taylor expansion in the first order with epsilon. So you will get this following expression here. This term is totally independent of B, as this is the tunneling time for the PT symmetric system, which is independent of B. But you will get another system which linearly depends upon B, any other terms which linearly depends upon B. And you see that when epsilon equal to 1, then this terms goes away, this terms goes away, and you get the same situations of this of the PT symmetry case. However, when epsilon is not equal to 1, you see that the Hartman effect is not there. The tunneling time in the limit of large B depends upon the thickness of the barrier. So when PT symmetry is broken, the Hartman effect is lost. And this calculation is extremely non-trivial because it's not doable, but because this you have to deal with the very lengthy terms. In fact, this K0 terms has more than 50 terms in that. So we don't see any Hartman effect when PT symmetry is broken, and Hartman effect occur only when PT symmetry is restored. So this case study shows that Hartman effect occurs when the PT symmetry is respected, and we do not know that whether this is a general result, as this study is only for the case studies of a simple PT symmetric system. However, as you also know that the real barrier, as it's found that for the case of the real barrier, the Hartman effect occurs actually. So what about the real barrier which does not has PT symmetry? And in the next slide, possibly, I mean, you are going to believe that the real barriers too can respect PT symmetry in the limiting case. Consider this PT symmetric system, U plus IB and U minus IB, which is a single PT symmetric cell. Now I put this single PT symmetric cell in a finite support, in a fixed length L. I put a total number of n such cell in such a way that this entire system remains PT symmetry. As you can see that this system remains PT symmetry, and the length L, if there are the n system, because each unit cell is having the thickness 2b, so the total length is n equal to 2nb, but I'm keeping L as fixed, and then I take the limiting case of this system as n tending to infinite. In this limit, what will happen that as you take n tending to infinity, the thickness of each cells will become infinitesimally small. and this plus IV terms and minus IV terms, as the wave passes through it, the gain and loss part of that will begin to nullify each other. And what you will get is the limiting case of this system in the limit of n tending to infinity, provided you have a finite fixed support here, L, is equivalent to a rectangular barrier of height U, which is U here, because plus IV and minus IV cancel each other, it becomes equal to the and the length L. So this system is equivalent to a real barrier, real rectangular barrier of width L and height U. And we have proven this mathematically, and the details are available in our paper in the Zero Physics Journal Plus. And we also calculated the tunneling time from the system, and we took the limiting case as n tending to infinity and b tending to 0, the tunneling time for the n cell for the case when n tending to infinity and b tending to 0 in such a way that the product of this remains equal to, it gives L. And this, we get the same expressions as the tunneling time of a rectangular barrier of length L. And because of this L, if L is large, the system respects Hartman effect. So the Hartman effect from a real barrier could be due to the PT symmetry in the limiting case. So this is what is our conclusion is that. So, I mean, even though this system, I mean, if you see it in this way, it does not have any PT symmetric component. But if you represent this system in this way, keeping n tending to infinity, in all means, this system is PT symmetry. And however, there may be a way that, I mean, someone can comment that you can.
Sorry, I have a question.
Please go ahead.
So in this limit, does also V goes to 0, or why does it disappear? I didn't understand that.
No, V does not goes to 0, but what is happening is that when the B, the thickness of the barrier is tending to 0, and in this limit, the plus IV and minus IV start nullifying each other as the wave propagates through it. So if you calculate the transmission coefficients for this system and take the case of n tending to infinity, you will get the transmission coefficient equal to the of a rectangular potential barrier of height U and thickness of this system. Is that clear?
Yes, thanks.
Okay. So, I mean, it can be commented that a real barrier U plus can also be represented as U plus IW, where you take W tending to 0 for the complex representation of the real barrier of height U. It is just a very simple actually, but this is not PT symmetry. The present system is PT symmetry, but if you have this, like, I mean, you can always say that a real number is the, I mean, is the generalization of a complex numbers. When the complex part is, imaginary part is 0, then you have the real number. But even though if you say this is not PT symmetry, but this representation is PT symmetry in which the imaginary component, the gain and loss component remains finite. Now, if you calculate this, I mean, in this case, I am relaxing the conditions of the fixed support L. I'm saying that there are just any unit cells are available, such that we don't have the conditions for L fixed. So that if you take B tending to infinity, the systems also becomes, the spatial extent of the system will also becomes infinite. And in this limit, if you calculate the tunneling time of the system from this system, what you will get that you will get an expressions which is independent of the thickness B as well as the number of the barrier itself. And what these expressions could be equal to, it is just the same as the tunneling time from a single cell in the limit of large thickness. So what we get is that the tunneling time from n cells in the limit of the large thickness of the unit cell is the same as the tunneling time from the single cell in the limit of the large thickness. And this is the graphical representations for the same, which you see that there are the different n values here, which is plotted with respect to B, and this is the tunneling time. And this is the theoretical limit here. This black line is the theoretical limit, is this expression. What you see is that all curves for larger B overlaps to each other, which means that for other cells, it doesn't take time to cross the barrier. So let me discuss the special case of our layered PT symmetric system in which we put the real component at 0, so that you have this system as plus IV and minus IV. This system remains PT-symmetric if you arrange it accordingly to this. And in this case, again, keep the support L as constant. So keep L finite and take N to infinite. B will diminish because 2NB is equal to L. As you take N tending to infinity, to keep this product constants, B will tends to 0. And these gain and loss mediums will become infinitesimally thin. And then a wave is passing through here, and you're calculating the tunneling time for this system. In this limit, N tending to infinity, B tending to 0. For this, if you calculate this, the tunneling time, you will get this expressions L upon 2K, which is nothing but the free propagation time of a particle to cross the barrier L as no medium is present at all. In the chosen unit, the velocity of the particle is just 2K. So this is L upon 2K. So the particle doesn't see the barrier at all in the limit of N tending to infinity and B tending to 0. So this results also shows the consistency of the stationary phase method in the appropriate limit, because we calculate this by the stationary phase method. We calculated these results, and what we are feeling, what we get is that there is no medium is present at all. This is the same case if you just take it as u equal to 0 in this case. But this is a different, I mean, the interpretation of this could be different, because that means you can also say that an empty space of a finite length is also a PT-symmetric system in an appropriate limit. But I do not have enough argument to, I mean, to strongly say that. I'm still trying to investigate this fact. So here is the two general results for the Hartman effect, which we recently came across. Consider this a potential. This so far Hartman effect has been studied only for this case of the rectangular barrier and the triangular barriers and the periodic case of the rectangular barrier, actually this. But what kind of the potential system respect this Hartman effect? This we were trying to investigate. So what we found is that if for an arbitrary potential Vx, if a unit cell system shows the Hartman effect, I mean, if for this potential the tunneling time is independent of the thickness of the barrier, is independent of P, then this is also true for the periodic case of that. So if a system, if a unit cell potential shows Hartman effect, then its periodic system will also show Hartman effect. And this work is recently published. And this result has been previously noted for the rectangular barrier, but we have proven this as a general result, that if an arbitrary potential shows Hartman effect, then its periodic system will also show Hartman effect. And recently we have completed a proof, we are not yet communicated, which shows that any smooth one-dimensional potential which is confined over a closed interval B, such that the potential value at the end point does not depends upon the interval B, then such system will always show Hartman effect. So overall, the conclusion of this, I mean, of our work is that the initial results indicate that the PT symmetry may be playing a role in the occurrence of this Hartman effect. And if we visualize the rectangular barrier as the special limiting case of a PT symmetric system, then this is also true for the real rectangular barrier. And a real rectangular barrier can be represented as a limiting case of the PT symmetric system. And these two results I just have indicated in my previous slides, that if an arbitrary universal potential shows Hartman effect, then its periodic system will also show Hartman effect. And this is, so thanks for your kind attention.
Okay, thank you, Hasan, for your talk. We can take a couple of questions.
I have a question.
Yeah, please go ahead.
Hi, sorry, maybe it's a basic question, but when you talk about tunnel effect in normal quantum mechanics, you usually think about the energy of the incident particle being smaller than the potential barrier. So since you're using complex potentials, so which condition on the energy do you use in your
Yes, so
calculation?
it goes with the real part of the potential.
Okay, thanks.
Any other questions? You can unmute and ask directly if you have any question. It seems no other question. So let's thank Hasan again for his talk.